This video is going to show you how we can demonstrate some of the properties of alpha, beta and gamma radiation in school. Let's start off by looking first of all at what our radiation sources look like. What I've got here is the alpha source. You can see that it's kept in a small lead-lined container there. That's in order to stop the radiation from getting to the outside world. You'll also notice that I picked it up using tongs. That's a safety feature. That's to ensure that my hand doesn't go anywhere near to the radiation. So, how can I show that there's radiation coming off from this? Well, you should remember that alpha, beta and gamma radiation cause ionization. So I'm going to use something here called a spark counter, which will pick up the radiation as it comes off and cause a spark. And there, as you can see, as I move the alpha source close to the spark counter, you get some sparking going on there. Move it away and it stops. What you might also notice is that sometimes you get some interference on the video. That's because of the spark that's being created. So how are we creating the spark? Well, the supply that I've got here is a 5,000 volt supply. And the spark counter consists of this grid on the front surface, and just below it, a few millimeters below, there's a very thin strip of copper foil. Normally, the voltage isn't quite high enough to cause a spark, but when we introduce some ions into the gap, and remember, ions are charged atoms, aren't they? So when I introduce some ions into the gap, it can cause sparking to occur. So what's causing the ions in the gap? Well, that's the alpha radiation that's coming off this source here. You'll notice that as I move it slightly further away, it stops. And it's a very sudden stop. It's not just a case of it gets a bit less, it gets a bit less. I move it in closer, it starts, up, and it stops. And that distance is about 5 centimeters in air. Alpha particles will only travel about 5 centimeters in air. If I get a piece of paper, place it into the gap there, you'll notice we don't get any sparking. Take it away, and we get the sparking again. Alpha particles are stopped by paper. Having used the alpha source, put it back into its container, of course, close the lid and we'll shut that down. My next source of radiation is the beta source. In this case, it's strontium 90 is the isotope. Again, you'll see that it's kept in a lead container. Handling it again with tongs. And by handling it with the tongs means that my hand is further away from the source, so being exposed to much less radiation. If I bring that up to the spark counter, you'll see that nothing happens. That might be because there's no radiation coming off this, or it's possibly because the beta radiation isn't ionizing enough to cause the spark counter to react. So what I need is a detector that's a bit more sensitive than just a spark counter. And for that, we use a Geiger-Müller tube. So what I've got set up now is the Geiger-Müller tube, the GM tube here, and that's connected to a counter. When people talk about a Geiger counter, what they really mean is this thing here, the Geiger-Müller tube. Now, since I've switched it on, you can see that we've already got to about 29 counts on that there. That's because of something called background radiation. If I just move away the beta source, just to check that it's not coming from that, you can see that it's still slowly counting up. Background radiation is because of sources that are all around us. Could be within the air, could be material that the bench is made of, could be some from the wood on this stand itself. You'll notice how it's a random count that we're getting here. You maybe get a while when there's nothing, and then you get a couple of counts together or so. If we left this on for a few minutes, then we'd probably find we've got a background count of between 20 and 30 counts in a minute. When we're doing practicals involving radiation, we always need to take account of the background count and be aware that it's there the whole time. Right then, let's have a look at the radiation coming off from the beta source. This was the source that I had before that the strontium-90 couldn't detect. If I place it in front of the GM tube, in front of the Geiger-Müller tube, you'll see there that it's counting up very quickly. So no, it wasn't a case that there's nothing coming off it. In fact, there's far more coming off it than from the alpha source. The reason why the spark counter wouldn't pick it up is because beta radiation is less ionizing than alpha. Of the three, alpha radiation is the most ionizing. Beta is in fact the one in the middle. Less ionizing than alpha, but more ionizing than gamma. Right, so let's see what can stop beta radiation. Well, if I place it into this holder here, in fact, it's a bit awkward going in, but hopefully that will stick. There we go. Then now it means that I'm not having to be so close to it. And we'll just try the effect of distance. So as I move the GM tube further away, you can probably see the rate at which it's counting is getting much less. This is two reasons. One, because the beta particles are more spread out as they come out, so we're picking up a smaller proportion of them, but also some of them won't be getting quite this far in the air. Unlike alpha particles, which would only travel about 5 centimeters and then stopped, beta particles will travel up to a meter or two in air and will tend to die away. So you'll get fewer and fewer and fewer, and then you'll get far enough away that you're back to just the background radiation. Okay, so beta particles will travel much further in air. What else will stop them? Well, I've got here some thin aluminium, just under 0.5 millimeter thick. Place that in the way, and you'll see that the count has gone down, but is still going up way above background. So, thin aluminium reduces the amount of beta, but doesn't stop it. If I go for thicker aluminium, so here 2 millimeters of aluminium, it's picking up a bit, but you'll notice it's been reduced by quite a lot compared with what it was. Beta particles are stopped by a few millimeters of aluminium. If I bring up the 3 boxes of radiation source that we've got, put them there. This was the alpha source, the one that we saw at the start. This is americium 241. If I place the GM tube next to the box, you'll see that I'm getting no more than the background count. Put it next to the beta source, strontium, and again, coming out of the box, seems to be no more than the background. The third source, which is cobalt 60, you'll notice I'm getting a notably higher count than background. That's because the cobalt 60 is giving off gamma radiation. Gamma radiation is the most penetrating of the 3. It will pass quite easily through the thin lead container that we have this in. So although the lead cuts out some of it, it by no means cuts out all of it. If I bring the gamma source up to the GM tube, you can see that it's quite active, but seems less active than the beta source. It could well be that in fact most of the gamma radiation is passing through the GM tube and not even being detected. So if I put the source into the holder here, then we can see what actually stops gamma radiation. So with the gamma source in the holder there and the GM tube in front of it, if I place the thick aluminium, which was stopping beta particles, in front of it, we see that it makes no difference. Gamma is not stopped by aluminium. In fact, as I said before, what you need to use in order to stop gamma radiation is fairly thick lead, and what I have here mounted on this is about 5mm thick lead. Place that in front of it and you might just about be able to detect a small reduction in the count. So, gamma radiation, the most penetrating of the three, will pass through thick lead even, and certainly up to several meters of concrete, is the least ionizing of the three.